9 out of 10 students walking into their IGCSE computer science exams are literally leaving guaranteed marks right there on the table. And honestly, it's not because they aren't studying hard. It's because they're falling into a trap. So in this explainer, our mission is pretty straightforward. We're going to rescue those lost marks by decoding the exact expectations of the Cambridge 0478 mark scheme. Let's get right into it. I want to show you this mistake before you make it yourself. There is a staggering 90% error rate on what absolutely should be the easiest part of the whole exam, converting binary to denary. Students just confidently write down their final sum, totally unaware that a silent, tiny error just completely killed their grade. Okay, let's dive into this. This is what examiners actually call the confident error. Just imagine a student trying to convert an 8-bit binary string into a denary number purely in their head, just using mental math. They're staring at the ones and zeros, trying to juggle those powers of 2 in their brain. And, well, what happens? They miscalculate the 8 or the 16-bit positions. Because they skipped drawing the physical grid, that final sum is wrong, and boom, they score an absolute 0. Let's rewind a bit and rebuild this the right way so you never, ever make that mistake. The absolute only way to guarantee your marks is to physically map out those 8-bit binary headings right on your paper. We're talking 128, 64, 32, 16, 8, 4, 2, and 1, placed directly beneath their base 2 powers, so from 2 to the power of 7 all the way down to 2 to the power of 0. This right here is the bedrock of what we call the no-mistake method. So here's that full no-mistake method in action, working all the way down to the hardware's logic gates. By taking the time to physically write out this place value table and mapping your binary bits perfectly into the grid, you're doing exactly what the examiner is begging to see. And here's a huge examiner secret for you. Showing these exact addition steps, that actually secures you partial marks, even if you make some tiny, silly arithmetic slip when calculating the final total. Now, what's really interesting about this is the fatal start with 1 trap. I mean, think about it. When we count in everyday life, we naturally start at 1, right? But in computer science, whether we're talking CPU registers or IP addresses, counting always starts at 0. If you forget that 0 is actually a valid and totally necessary digit for placeholding, you're going to misalign your entire grid, and the whole calculation just completely falls apart. So let's lock this in as a quick, snappy, 3-step mental routine that you execute the literal second you sit down for that exam. Step 1, build the place value table. Step 2, map the positional values perfectly underneath. And Step 3, calculate the final total, but remember, only add the columns that actually have a 1 in them. It's just a totally bulletproof mechanism. All right, let's shift gears a bit. We're going to see how this same need for precision builds right into our next high-stakes topic, which is networking. Because just like binary conversion, networking definitions demand absolute exactness. Take the term autonomous computer, for example. Now, simply put, it just means a computer that operates on its own, making its own decisions. But the mark scheme's safe definition, that is a device capable of sending or receiving data between processes on remote machines entirely without external control. You absolutely want to memorize that exact phrasing. Understanding this network anatomy really reveals the clear difference between dropping a weak, generic answer and a high-level mark-scoring one. A weak answer is going to say something like, oh, a network connects computers to share things. Honestly, that scores maybe 2 out of 10 marks. But if you use our answer upgrade template, a high-level response specifies that it connects autonomous computers using specific protocols to share resources, like, say, a centralized database, within a highly specific scenario environment. Seriously, grab your red pen for this because here are the insider examiner insights that separate the A-stars from everybody else. First off, you must avoid those generic definitions at all costs. Second, always use the specific scenario nouns that they actually give you in the exam prompt. And third, apply the concept mechanism advantage framework. It's simple. You state the concept, explain how it mechanically works, and then give the advantage but tie it directly back to whatever scenario is in the question. Now, applying that exact same precision to data transmission, we've got to strictly define our modes. Simplex, that is one way only. Data travels from the sender to the receiver, and that's it, period. Full duplex, however, is a two-way simultaneous flow. Data is traveling in both directions at the exact same time over the exact same channel. And this brilliantly illustrates a highly intuitive way to actually grasp this, the road and traffic analogy. Think of simplex as a strict one-way street. Half duplex is more like a single lane where cars can go both ways, but crucially only one direction at a time, kind of like waiting at one of those temporary construction traffic lights. And full duplex, well, that is a multi-lane superhighway where data is just flowing in both directions simultaneously, zero collisions. So here is a quick challenge for you to mentally rehearse right now. Can you apply the 4-prompt recall method? That's what, how, where, and why to a specific data transmission scenario? Like if the exam suddenly asks you about a walkie-talkie, ask yourself, what is it? It's half duplex. How does it work? Two-way, but sequential. Where is it used? Voice communication. And why? Because the channel just can't handle simultaneous audio overlap. Using this framework makes your answers infinitely adaptable to whatever they throw at you. As we pivot over to hardware and data transfer, I want you to remember this golden rule. Precision beats short labels. Full marks require technical terminology, not just naming devices. Listen, sloppy vocabulary will absolutely destroy your grades when you're discussing system architecture. You really can't just name-drop components. You actually have to explain the underlying mechanics. Which brings us right to mastering hardware buses. To guarantee your success here, you need to follow a 4-step mastery path. Notice the absolutely critical distinction we're highlighting between memory, like your RAM, and storage, like a solid-state drive. When a question pops up, you must first diagnose the demand, then define the specific bus, whether you need the data bus or the address bus, explain its sequence, and then, you guessed it, anchor it right back to the specific scenario they provided. Now, to actually memorize all these complex hardware interactions, you need a bulletproof strategy. Enter the 3-pass revision cycle. Pass 1, secure those definitions. Pass 2, rehearse the diagrams until you can literally draw them from memory. Pass 3, adopt to exam scenarios. You don't want to just passively read the textbook here. You need to visually map out these interactions and then practice applying them to fresh problems. Okay, let's simulate some high-pressure exam conditions right now. You've got 10 seconds. Try to spot the fatal error in this simulated binary conversion that is totally going to cost the student their grade. The clock is ticking. Test your visual pattern recognition. Ready? 3, 2, 1. So the crucial point is, did you catch it? The student calculated 16 plus 2 plus 1, right? But they completely misaligned the place value for the 1 bit in the 16 column. It actually should have been mapped under the 32 column. Just a tiny little slip, but a massive grade drop. But hey, with that no-mistake method we talked about, you're never going to do that. Next time, we'll actually look at the hexadecimal shortcut to make handling these really large strings even faster. Ultimately, if you master these basics, you unlock the entire syllabus. Every advanced networking protocol, every complex hardware bus, it all fundamentally boils right down to these simple ones and zeros. If this explainer helped these concepts finally click into place for you, make sure to subscribe to Ace the Exams at acexams_IGCSE and get ready to absolutely dominate your next paper. So, what topic should we decode next?